and just show briefly why propensity score weighting makes some sense. And weighting regression makes a little bit of sense. So I'm just going to take these two. Maybe I'll only take one of them and go through what the math shows us. All right, so if we just set d equal to 1, looking at the average treatment effect. So we've got the average treatment effect calculation, and we're just plugging and chugging out some numbers, and we're conditioning on treatment status. Sorry. Oh, yeah. So the conditioning here on d is equal to 1 requires me to multiply by the propensity score on the outside. And then basically we're sort of plugging and chugging. And we end up at the end with the sort of expected outcome given the x's and the treatment status. So just a sort of simple, reasonably simple rearrangement of the terms shows us that this weighting structure actually is what we want it to be. Do the same thing now only by setting d equal to 0. We've got the same sort of basic argument. I'm conditioning on d is equal to 0, so I'm multiplying it by the probability that d is equal to 0. And in that case,
Hmm? I was just saying that I think was that an error where there's 1 minus the weighting?
wouldn't that be an error? No, I have made a mistake somewhere. Now I'm not sure where. This should be 0 here. Yeah. Yeah. So once you replace that with 0, then it does go away as you need it to. And we end up with the expected outcome given the x's and the d is equal to 0. And so the difference between those is, of course, the average treatment effect that we want. So this basically shows us that in principle the average treatment effects can be calculated from this weighting structure, which is really all I wanted to get across. I'll skip through the integration version of that. And the only thing sort of worth knowing is that the difference between the average treatment effect on the treated and the average treatment effect overall is that the average treatment on the treated has to be essentially reweighted by the propensity score divided by the underlying probability of treatment in the data. And so it's a small adjustment to these according to the weights that are here, right? Okay. But more generally, this is how you think about doing this. You estimate the propensity score, and you create 2 different weights. One for treated people, 1 divided by the estimated propensity score, and for the untreated people, the propensity score divided by 1 minus the propensity score. And if we're doing for treatment effect on the treated, we weight all the treated individuals at 1, and we weight, all the untreated people by 1 over 1 minus the propensity score. And this, by doing this, we've got the weights that we need, and then we simply estimate the mean. But we estimate the mean by essentially running a regression on the outcome using the weights with just the intercept, right? And that gives us the intercept and the treatment status, excuse me. And that gives us the gap between the underlying mean and the treated effect mean. Okay. So anyway, as I said earlier, these estimates can be bootstrapped. So it's very useful. We can go through the process, we can do the bootstrapping, and we can estimate this. If you really, really want to, you can jump into the world of machine learning. Instead of using a probit or a logit, you can start asking questions about, well, what's the appropriate functional form for the propensity score model? And so there's a little bit of literature in sort of double robust estimation by, what's his name? It's a really nice Russian name. He's based at Yale. That does a lot of these sort of fairly complicated things. So, yeah, you can sort of take this a little bit further, and like I said, apply machine learning models to the underlying propensity score if you really want to. And then that potentially throws out variables that don't matter, and some of the things like that. Okay, so let's think a little bit about an example. This is I guess not the kind of thing I would necessarily do something with. Okay. So in R, there's this match it package, and Noah was nice enough to actually explain to us how we should do this, right? So tells you a number of things about maybe how we should develop statistical models, tells us what package we need, and then it goes to a very famous data set from a fairly famous paper by Lalonde Lalonde is the original paper. It's this randomized controlled trial, in fact, that looks at National Supported Work Program to see what kind of impact that had on labor market outcomes in the U.S. All right, and a paper afterwards used this same data to show that if in fact you've got a randomized controlled trial, matching does a really nice job of estimating the treatment effects. Now that might not be that surprising, but matching itself is supposed to be conditionally exogenous, right? So if you've got randomized controlled trials, which are exogenous, you would expect this sort of approach to work fairly well. So anyway, so it describes the data and then talks about how to, what's the effect that you want to try to estimate. All right, so target population should be the one you want to try to generalize on, and we're going to try to estimate it in a sample that generalizes to the population, right? So this is sort of standard statistical kinds of thinking, and a few other things. All right, but then it talks more about practical issues. So the first thing that people do, remember, one of the assumptions is balance. So let's see how different the treated sample is from the untreated sample, right? So they call this checking initial imbalance. Right, and so basically what they say is use the match it command and look at the difference in outcomes using distance based on the propensity score, right, which is a GLM estimator in R. So, and then it gives us the answer, right? So the mean distance treated 0.57, control 0.18. If I've got this means treated, means control. Oh, standard mean difference. So this is the difference itself divided by the standard deviation, which is a common way to think about it. So it basically just shows us at the end of the day that a lot of these variables are pretty different, right? And that's kind of what we want to get across here. So the initial data, the treated individuals are fairly different from the untreated individuals. And this is a fairly small sample, right? Plus minus 600, 610 people, right? Okay, so you would not compare the means in this sample because the underlying samples are different, right? So what we want to try to do with matching itself, or reweighting if we're doing weighted regression, we want to try to, we want to do some matching. All right, so now you're using a method to do some matching. This is nearest neighbor propensity score matching. So again, we've got the distance measure, which is the propensity score, same data, basically the same quote unquote regression. All right, the difference in formula is quite small. But here, in the initial data, no method at all was applied. You were just looking at the data itself to see how different it was. Now we're applying a nearest neighbor matching. There are other matching methods in this package. And it shows you what it gives you. It tells you what the method is. It's one-to-one nearest neighbor. It's using the propensity score, which is estimated by default with the logistic regression. You can change that. It's estimating the average treatment on the treated. You've got 614 total observations, but only 370 that are matched. Okay, but with 370 matched, it's actually 740 observations. Okay. So this is one thing that happens when you match, at least in principle. You've got data that, so if you're taking all of the treated individuals and you're matching them to somebody that's untreated, the untreated might get used multiple times. And so the underlying matched sample isn't the initial sample. It just isn't. Okay. All right, so how good did it match? Well, let's just look at balance. Right, again, balance is an important feature, so let's see how good it does. Is it great? Maybe not perfect, but the propensity score differences now are much smaller. This before was 0.18 or something like that, so this is now much closer. The age difference was bigger. The education difference was bigger. Right? The race differences are still kind of big. Okay, so it doesn't do necessarily a great job of matching across race, but many of the other things match much better than they did before. Okay, so after matching, this is an improvement. And it talks a little bit about it. It says, all right, we can plot the propensity scores. I don't really like this plot. I'll show you one I like a lot better. What this is trying to do is tell us something about overlap. Right, so it's just a plot from sort of 0 to 1 of the underlying probability of being treated and the underlying probability of being untreated in the data. Right, and I look at this, right, there's huge holes in this data in the middle. Right, so this is not necessarily the kind of data that you would say, oh, well, let's match across the whole data. If it was me, I would say, well, let's match around here. Let's match around here, and let's look at what's going on in sort of the two ends of the distribution, because there seems to be some useful overlap there. I'm a little skeptical of what's going on in the middle. It's myself, right? But it does show you that there is overlap, right? From 0 to 1, there are propensity scores for both treated and untreated. Okay, so it meets the underlying expectation of having propensity score overlap. So we've got better balance, not perfect, but better balance. We've got overlap, okay? The ignorability condition, we just assume, right? We can't do anything about it. And then it plots these different things a little better. So I'm going to find these maybe a little more useful. But now it starts to plot different components of the distribution. So this is the age distribution, the matched distribution relative to the overall, the distribution of married, the distribution of the different variables that are in the data. All right, so you get some idea of what the data looks like. It does okay. Then it suggests, well, let's try a different matching specification. Do the same thing. Now we've got way better performance, right? The distance is better, the age is better, right? So it's showing you from a practical perspective, here's one model. It matched better than than no match, but it's still not great. Now here's a slightly different model. It matches even better, right? So this is a little bit like what they tell you not to do, which is let's try the kitchen sink, okay? But this is, with matching, this is what we're doing, right? We're trying to get the two different groups to look as much similar as possible. It's not necessarily meant to be some sort of really well constructed theoretical argument. It is, how well can we get these groups to match? How much balance and overlap can we get? Okay, so it's okay to throw in the kitchen sink. You might think that's a bad idea, but we don't care. Right? We want the behavior to match the assumptions. So that's what we're after. Like I said, we get much better behavior here, and you see kind of that being shown more generally. All right, and then we can show a little bit about, yes?
I just wanted to, so we're doing the matching to try and get it, we're trying to...
You're estimating a propensity score, right? And the model you use to estimate the propensity score has, different variables that you include, okay? And what this is showing you is that in one model, you got, and then you compare the balance of the data, right? So one model wasn't giving you great balance, but it was better than not using any model. And then they revise the model a little bit, and now you get really nice balance. Okay, so all this is really showing you is from a practical perspective that the model can affect the underlying performance from a balance perspective, which underneath all of that is this idea that we're matching people, right? So answer your question.
I was trying to understand. So this is us trying to almost imitate like the random control trial procedure.
Mm-hmm. That's the goal, right? The goal, and if you read an RCT paper, one of the first things they will show you is that the groups are balanced. All right. So that's where the similarity is with RCTs. It's about the idea that the groups don't differ in some way that we think might matter. Right? So if you're running an RCT on I don't know, some sort of smoking cessation thing, and all of the people you're treating aren't smokers, it's kind of a stupid RCT, right? So you need that sort of balance. You need, some of them have to be smokers so they can potentially quit, right? So that's it's the best example I could come up with at the moment. But yeah, that's what we're after. Okay, so it shows you a couple of other balance things that it will produce for you, other sorts of plots it will produce for you, all right? And then, I think Matt's already talked about this, the marginal effects package. All right, so here the idea is now we want to figure out what the underlying impact is. All right, and so you've got a model where we're trying to understand the underlying outcome as a function of treatment status. And here they're allowing for interactions. Okay, so this is a little bit more complicated than the simple treatment status, non-treatment status. Okay, but you could certainly estimate that version of the model, and I show you example. I have an example later on. And then when you fit it, you use the actual match data. Okay, you don't use the initial data, you use the actual match data, and then you fit with the weights, right? Remember, we've got this weighting idea going on in the background. We've taken the propensity score to re-weight the data. So, and then you're essentially creating a series of comparisons using this model based on the treatment status. You're calculating a covariance based on subsets that are treated or untreated. Okay, so this is part of the command structure, and it gives you really useful sort of distributional differences, right? And so it talks a little bit about what you can report and so on, right? So this is just a really nice guide that you can use to sort of estimate a propensity score model. Okay. So I take that and I apply it to some South African survey data, the living conditions survey data from 2014-15, but the reference is 2017. And I'm going to estimate something called the cost of the first child. So there's this literature that tries to understand child costs as well as equivalent scales and a few other things along those lines. And so the idea is how much more money does a household with one child spend on average than a household with no children, right? That's sort of the basic question. But here I'm going to base it on something called minimum income. So there's another question in the survey, which is what's the minimum amount of income this household needs to get by on a monthly basis? So I'm going to use that as my cost measure. All right, so basically the regression is what's the minimum cost as the function of a treatment status, where the treatment status is there's one child in the household or no children in the household. And clearly there are big differences, right? So very old people rarely have children in the house. Maybe I shouldn't say very old people. But when you get to sort of a certain age, the kids leave. They're tired of you, right? Or you're tired of them or something like that. And you kick them out. So, maybe then when you get to be grandparents, you take them back in again because you're over your years of pain with the original kids, or whatever it happens to be. So, I'm sorry, I'm making fun of things I shouldn't really, but it's always kind of fun. So I mean, there are certainly age factors related to whether or not you have kids in the household, and having kids in principle is at least partially a choice. Not everybody chooses to have a kid when they have the kid, right? But there are some decisions that get made along the way. So there's also likely some endogeneity. And so what we're going to do is, try to use matching as an approach to dealing with the plausible endogeneity and think about whether or not what this cost might be, right? So I'm gonna limit it to married couples or couples living together, even though certainly there are single parents with children. Okay, so I want them more comparable in some way. So I'm limiting it to married couples or those living together, and I've got this sort of simple treatment of one child or no children. All right, and I just want to know what the difference in this minimum required income is. So here's a couple of summary statistics from this data. I've got basically 2,500 observations, household head gender. All right, pretty much it's really quite similar across the groups. Household head age is different, right? This probably isn't that surprising. The slightly older household head is less likely to have a child in the house. There aren't big differences in either of these two, right? So even before jumping in, I don't actually expect much to be going on here, right? You don't run a model, let me rephrase. You don't develop a question and then sort of look at descriptive statistics and see that there's not much going on in the descriptive statistics and think, oh, by running this really cool model, I'm going to find massive, massive results, right? Descriptive statistics go really, really far to telling you whether or not there's any real need to continue, okay? So if I was really doing this as a research question, I would stop right here. Right. That difference isn't big enough for me to care about, and there's not enough going on in the rest of the data for me to think this really matters. Okay? But having said that, this is still a useful sort of exercise in how this gets done. All right, so here's the variables I'm going to use. I'm going to use overall household expenditure as a control. I'm going to use whether or not the household head is a male. I'm going to treat age as a factor. So I'm going to use every single year of age as a dummy. Right? So I'm not going to use age and age squared. I'm going to use this sort of longer, simple dummy structure. Sort of rural, urban, formal, settlement kind of questions, province, ethnicity, and this sort of marital status I'll separate. Married from those living together, right? So it's not a lot of controls, but at least it's some. So here's the initial sort of results. And this just shows me the overlap in the underlying propensity scores, right? So for those who have no children, their estimated propensity scores are in pink, I guess. I don't know. Some color like pink. Coral. Coral. Let's call it coral. I like that. And here the propensity scores for one child are in cayenne. I'm going to use that one. So it's a turquoise bluey kind of thing, right? So those are the two colors we've got. And you can see certainly there's overlap. But at the same time, you would say, oh, these households are really different, right? There's no overlap here. There's a big gap here, right? So the first thing I would do is I would eliminate this side of these two sides of the distribution. So I would take every propensity score that's sort of above 0.85, maybe, I don't know, whatever that number is, and I'd throw them out. Okay? It's only going to eliminate a couple of one-child households, but fine. I'm going to eliminate all of them below 0.1, give or take, right? I'm going to throw those out. So now I'm going to deal with the smaller sample than the initial. Because in my view, there's no overlap for those subsections of the data. Okay, and I don't want to make comparisons across households that don't overlap. Okay, I don't think that's a good idea. I can, there's nothing stopping me from doing it given the assumptions in the story. I just think that's a bad idea. Okay, so I do that. I don't show you the revised picture, but it doesn't obviously look that different. You can tell obviously that a couple observations fall away. Okay, so this is, I've not matched, this is just the initial propensity scores. Okay. So this is what I just said, all right? I've got plenty of overlap. I've got scores are different. Actually, this is what I mean by scores are different, right? There's sort of a clear story. Households here, and you kind of expect this, right? There's a fairly clear statement about these kinds of households are less likely to have a child. Whatever these types of households are, they're more likely to have a child. It's not like perfect overlap, right? Where the distributions look the same. Okay? They look different, which at least says that there's some value in the propensity score regression because they are separating the households a little bit. All right? So whatever it is I'm using as controls are creating some separation. and that suggests that I can reweight the data in some way, right? Okay. Oh, I do actually throw some of these out. So let's look at the balance. So this is again, this is before matching. This is log expenditure across the two types of households. Right? Not much difference. Right? Overlap. It's not about overlap here because I'm not looking at propensity scores, but it says that they're really quite similar, right? So the pre-match balance when it comes to log expenditure isn't very different, okay? We saw that earlier on the descriptive stats table. We also saw this earlier on the descriptive stats table, right? There is a difference in age, right? It's the generally younger people that have kids in the household than the older people. You might ask me why I would include somebody at 90, right? That'd be a fair question, right? I didn't sit down and think really hard theoretically about sort of where I should put this. I just want an example, okay? But yeah, you would probably look at this and say, well, you know, it really starts getting unrealistic. Not that they don't have, obviously there are people at this age with one child in the household, but, and by child I mean somebody under the age of 14, but you probably would be interested in sort of households that are a little bit more nuclear, right? So mother, father, child, as opposed to grandmother, grandchild, right? You might want to separate those households in doing the analysis, okay? Because I do think grandmother, grandchild houses are different than somewhat nuclear households, right? So I would separate the analysis if I was really, really thinking about this. Okay, so I don't show some of these other ones, but if you look at the data, you do see some differences in the propensity score. You do see some differences in age of the household head. You see some differences in gender of the household. You don't see much difference in log expenditure. I don't provide you an illustration of all of those, but there are some differences. Okay. So let's match it in the background. But here's what the match sort of tells me. I'm matching 2 to 1. Nearest neighbor with replacement. I'm using a caliper, so I don't want my matches to be too far apart, so I'm forcing that as well. Sorry, it doesn't quite print out correctly. I've got 2.7 thousand observations. I end up with 1,873 matched. So it's okay. And I'm using the propensity score with a caliper and common support, using again a logistic, but I could choose to do a probe it if I really wanted to. Just kind of following that web page I showed you not too long ago. Okay, so once I match, here's now my propensity score. There's still, right, some differences, okay, but not the kind of differences we saw earlier. So I've thrown out the outsides, right? And I've matched the household, so now there's a lot more similarity across the propensity scores than there was before. Same with age, lots more similarity than there was before. And here's my underlying estimated treatment effects using inverse probability weighting, okay? So I basically run a regression with a simple dummy. Okay, I don't include all these other interaction effects. For now, just a simple regression. I get an estimate of 0.085 log points, 0.86 log points, which isn't very large. Standard error of 0.05. 0.08 divided by 0.05. Not really quite statistically significant, but close, right? It's about 1.6. Maybe 1.64. It might be right just at 10%. I didn't actually do that calculation. So what does that suggest? It says that the cost of a child is 0.0886 log points higher once we've done this correction. 0.086 log points, I don't know what that is. Someone wants to do a quick exponential of 0.08, I'd appreciate it, but you don't have to. It's not a ton of rand, but it's certainly some rand. I'm not 100% sure why I lost the standard error here. I didn't go back to double check because I ran out of time. The average treatment on the untreated is essentially statistically insignificant, and the average treatment effect overall is the average of these two, right? So you've got 0.086 plus 0.063 is about 0.15, right? And this is about half of that. Okay, so it's the average of the two. Okay, so not a big effect. Admittedly, slightly more than I expected, given the initial sort of data. The next thing I tried to do was see whether or not controlling for gender of the household head. So I interacted the dummy variable with the gender, just to see if there was anything there. And we get fairly similar average treatment effect on the treated, about 0.08. We get a much smaller average treatment on the untreated, but it's still statistically insignificant. So calling it smaller maybe is a bit of a thing I shouldn't do. It was insignificant before. It's still insignificant. Hasn't really changed. And then the overall average, right, again, 0.08 and 0.03 is about 0.011, 1112, right? And again, this is about the average. So that's what we expect it to be. Okay. So I have loaded the data I use this for, so you can actually replicate exactly what I've got if you want. Or you can try to do something slightly different, like look at the cost of the second child or the third child. I just haven't given you any code yet. Lunch is at 12, 1. 12
to 1.
12 to 1. So let's try this. There's the web page. Right, which is the Match It web page. It shows you sort of what to do, tells you what the code is. On the drive should be the data. It's an R data file. And see if you can replicate my results. Yes.
One thing I forgot to ask, how do you save these visualizations? If you want to now copy how do you like screen grab?
Okay, so when I do this, and essentially the main reason I switched to R in the first place was the ease at which this can be done. So just as an aside, I know this is really, really small, okay? But essentially these are all of my slides. Contained in my slides is something like this, which is a function to read in data, right? So all of my R code is contained within my document, and then I compile them together. And so the screen grab happens without me grabbing it from the screen, right? It gets built and then pushed in as a file, okay? But otherwise, you know, if you were to sort of run it outside of this structure, you would get a figure that you could save, right? You could actually save the actual figure, or you could do a sort of screen type grab and save it that way, right? But generally, I'd recommend saving the figure if you're not. I mean, this takes a bit of time, right? Because I work in LaTeX as opposed to, say, Word or something. But you can build Word files, HTML files, LaTeX files, PowerPoint slides, using this entire structure, right? And that's a side comment, but it does take a bit of effort to get comfortable with it. But here's my sort of favorite. Oh, that's a fly. It's okay. It's not going to sting you. There's two things that I think are really crucial here. One is, when you run a model and spit out some output, and I don't think people do this anymore, but they might. Don't take the output from the screen and transfer it onto a piece of paper and then type it into another file so that you've now got an Excel file with this, right? That's just a horrible idea because you're creating too many opportunities to make a mistake. So whatever software you use and get comfortable with, figure out how that software creates tables that you can directly import into whatever document you're going to write. Okay? This is lovely because I build a table inside of my paper. Okay? The next thing you absolutely want to do is create a structure that sort of has simple instructions. This is step one, this is step two, whatever. And then at the end of that, if you follow all of those steps, your paper's done. Okay? And the reason that's so nice is because at some stage, some referee is going to say, that's stupid, that's nice, fix it, right? And if it's all built in this way and you know exactly how it's done, then all you have to do is change that piece or that piece, and you can rebuild everything quite quickly, right? And I mean, it takes me in a typical R&R process, unless the analysis itself takes a long time, I can essentially recompile the paper in half a day and incorporate all the comments, right? Because all the tables are built already. I don't have to do anything else. It just builds me a pretty paper. And I say the word pretty I mean it. It actually looks very nice, right? And that's the other thing that really matters. I think it shouldn't, right? It really shouldn't. But if there's one thing that can look really bad when it gets, especially, so you submit something to a journal, the journal will then typically compile it into whatever it does to send out to reviewers. I have seen Word do some of the most ridiculous things in that setting, right? Whereas if you stick it into PDF, it almost never happens, right? So Word might be the absolute worst document writing document processor that exists. It's convenient for a lot of things, right? If I have to write a letter, writing a letter in Word's really easy, right? If I want to write a complicated paper with equations and figures and tables, no, right? Because I don't know where the table is going to end up next. I don't know where the figure is going to go. I don't know what's going to happen to the equation when I change the format of the text here, right? The changes over there, and then I have to fix it all, and I cry and I scream, and I want to break things, right? So with me, this is worth, if you really want to get into an academic structure, this is absolutely worth the effort. Well, LaTeX, or even, I mean, Stata does this as well. It's just not as good at it yet. And the reason is because R is entirely open source, just like LaTeX is, so they combine easier. Stata is not open source, and so its ability to to combine isn't as nice. But they have started over the last sort of 3 or 4 releases building the process that R has had for probably 30 years, maybe more. Right? And R is only like 40 years old. Right? So the convenience is there. I also, in my view, R's graphics are way better than Stata's, but you can build really nice plots in Stata. Right? And you notice I'm not using eViews as a word because I don't really know what eViews does. Right? But the one thing that drives me crazy is a journal editor. All right. So I think if you have lag operators in eViews, they use like question marks. I think it's eViews. And so people will submit tables in papers that have question marks as a variable name. And it's like, but if you've got a question over what this is, why are you submitting it? Right? It doesn't look right. And so this is the other thing that's really useful, right? So when you build a table, don't use a variable name that you know, right? So I mean, even some of my variable names, right? It's where's my table? Sorry, it's here somewhere. Yeah, right. LNX, HHH.mail. Province I'd be okay with. I think that's fairly clear, right? Most people would know what LNX is, okay, but don't let them guess. Say this is log expenditure, right? So when I write the table, right, I'm explicit about this. Log total expenditure, all right? And I recommend this over and over again to my students. Don't use variable names in tables, use short descriptors. Right? Panel models, right, for those people that love panels, right, time series panels. I get papers that say LNRQ. Right? And then I have to find some other set of definitions for what LNRQ is. That is a bad use of my time. Right? And as a reviewer, I don't like my time being used badly. All right, so here's the comment I'm making. Treat your reviewer the way you would like to be treated. You don't want to have to search for stuff in a paper. So don't make them search for it. All right? It might sound obvious, it might not, but these are really useful things, right? If you've got a table with a bunch of regression output, make sure that there's a footnote to the table that describes what equation to look at or other kinds of things, right? So if you read a paper from, I don't know, the Quarterly Journal of Economics, right? They'll be very specific about what variables were included in the regression, but they won't give you that output because that's not what the paper's about. Right, so don't give people output that has nothing to do with your story. Just tell them that that's what you did. It's okay. Less space is better. Anyway, but yeah, so I've put this data together. I want to give you the chance to work with it to try to sort of replicate my results so that you have some idea that you're sort of doing it correctly. All right, so I'm here. I'm happy to answer questions. I'm happy to help you. But we have basically 30, 35 minutes before lunch.